Can you all see my screen now? Can you see my screen?
Yes, sir.
Okay. Okay. So, as you know, this is the paper CC37 of your third sem, and we have to begin first of all by asking a question that we have already learned so many things about light and so on. We have learned quite a bit of classical mechanics. So why do we require to study a new topic which is called quantum mechanics, and what is it all about? So first of all, I'll quickly recap. Those who have already gone through my slides or read my notes uploaded in the LMS, this will be a recap for you, and those who are new in today's class, this will be new for you. So I won't rush through this. So the first question that we ask is, why quantum mechanics at all? Okay, and the answer to that, uh, well, the general answer, and this is what you find in Feynman's book, is that things on a very small scale do not behave in the way we are used to things being on a macroscopic scale. Okay, so when you see the movement of electrons or atoms, for that matter, and other subatomic particles, it is seen that their behavior is very much different from the behavior of, say, tennis balls or moving cars or trains or human beings. Okay, so so there was a requirement for a different kind of study, because people could not explain such behavior on a submicroscopic scale. And the fact that these particles, the atomic and subatomic particles, they are actually the building blocks of our universe. So knowing their behavior and what kind of science governs their behavior is of course of utmost importance. And it was at one point of time found that there is this division between the macroscopic and the microscopic scale, and we cannot generalize the theories and laws that we know about the macroscopic world to the microscopic world too, and a different set of laws are required to understand the behavior of particles in this subatomic scale. So that was one requirement that cropped up uh, from the studies and from the experiments done by some major scientists. And if you think about it, standing in today's time, in today's world, then the very fact that I am taking this class with you online on my laptop, and you all are listening to me, um, seeing my PowerPoint presentation on your, perhaps most of you are using mobile phones, um, that this very thing that is happening, we can say, is attributed to quantum mechanics, because it is because of quantum mechanics that solid state behavior could be studied in the microscopic scale, and it is quite different from what we know in the macroscopic scale. And it is because of the behavior of these solid state um, behavior. Someone's microphone is unmuted. Please, can you mute your microphone? So it is because of this behavior that is observed for atoms, that result in several unique features of the solid state, that, you know, semiconductor devices were studied, that chips, nanochips, integrated circuits were made, and the result is this great evolution, or I should say revolution in communication and solid state devices like our laptop or our mobile phones that we use. Okay, so that is the technical or industrial use. And apart from that, in core physics, you know that perhaps from your people who are interested in this, people who have done a little bit of Google search or read a little bit of physics books, you know how interesting, amazing and important quantum mechanics is. Okay, so let us dwell into a little bit of history. I know I've done this in our last class, but I'll quickly go through it once more. Is that Newton, defined light as a stream of particles called corpuscles, and he gave the corpuscular theory of light, which could explain reflection, refraction and shadow formation. However, experimental observations demanded wave nature, and we've discussed this in detail during our physical optics classes. You remember the classes that we had in the beginning in college. And so several people like Huygens and Youngs and Fresnel and Fraunhofer and Brewster and Malus, etc., they worked separately on different experiments and established the wave property of light. Okay, and finally it was James Clerk Maxwell who summarized the behavior of these waves and gave a general set of 4 equations, electromagnetic waves, and that basically summarizes the entire range of electromagnetic waves. However, remember, so all this proved that light is a form of wave, all right? But this was all pre-1900. All this happened before the year 1900. What happened post-1900? The first experimental observation that demanded a different kind of theory was black body radiation. Okay, and this is being done in detail by B.M. Sir in his quantum theory class. So we just need to know that black body radiation could not be explained by wave phenomena, and Max Planck, the celebrated German physicist, he introduced quantization of energy during exchange, and this was done in 1900. Okay, but then Compton effect was observed, which also could not be explained by wave phenomena. Electric effect was observed, which again could not be explained by wave phenomena. And finally, Einstein used Planck's hypothesis and he proposed the existence of a particle called the photon in 1905. He said that light under certain circumstances behaves as a stream of particles, and each such particle is called a photon, which has an energy h nu. All right, so light is not only a wave, it can also behave as a stream of particles, although both under different circumstances. So the conclusion from this discussion is that light is dual in nature. You cannot uh, exactly say that light is wave or particle. Under certain circumstances, it behaves as a wave. Under other circumstances, it behaves as a stream of particles. The universe is composed of, we know, either matter or energy, be it the planets or the spatial bodies or the asteroids or the stars. It is either matter or energy, and you also know from your general knowledge that matter and energy are interconvertible. So in the universe, there is no third item. It is either matter or energy. Okay. We already discussed that waves is dual in nature. So from the complementarity of energy and matter, we might as well say that matter must also be dual in nature. I hope all of you can hear me clearly because I don't have a very good voice today. Can all of you hear
Yes,
me
ma'am.
clearly? Okay. And please do
Yes, ma'am.
okay, and please do stop me and ask me any questions if you have in between, because this is majorly a one-sided class. I cannot even see you all, so it's pretty difficult in any case. Okay. So there was this person called Prince Louis de Broglie, a French prince who was actually studying medicine, but then he became very interested in his brother Maurice de Broglie's study of light as a stream of particles, the particle nature of light. And he said, no, this cannot be true for light alone. It must be that just as a moving wave can be thought of as composed of a stream of particles, similarly a moving particle must also have with it associated a wave. And he also gave a formula for the wavelength of such a wave, which was given by lambda equal to h by p, where h is the Planck's constant and p is the linear momentum. This was in 1924, so much later than when Einstein actually introduced his photon. It was almost 19 years later. Okay, so but this was only a hypothesis. However, this hypothesis led many scientists to design experiments which might establish the presence of such a wave that Prince Louis de Broglie was talking about. And one of the first people to successfully design such an experiment was Davison and Germer. Okay, so in Davison Germer's experiment in 1927, so 3 years after Louis de Broglie gave this hypothesis, they said that they actually observed diffraction like intensity pattern with electrons. Okay, so in Davison Germer's experiment, electrons were accelerated through a certain potential and made to fall on a crystal, and the reflected wave, when observed, reflected particles rather, when observed by a detector, showed that the observation could not be explained if you considered the electrons as particles. However, it was something like we observe in interference or X-ray diffraction, and that was possible only if the electrons behaved as waves. And following this experiment by Davison and Germer in 1927, there were other physicists who observed the Laue pattern for neutral diffraction. Now, what is Laue pattern? If you Google this Laue pattern, you will see that this is basically a pattern observed when X-ray is diffracted by certain crystals. So X-ray is an electromagnetic wave which, when undergoes diffraction by some crystals, show a pattern which is commonly known as Laue pattern. So it was seen that neutrons, which are actually particles, which are denoted as particles, those when are also reflected by when these neutrons are made to impinge on crystals, the reflected particles when observed show a pattern similar to Laue pattern, which is only possible by waves. And then Laue pattern was also observed for hydrogen atoms and helium atoms, both particles, but showed wave-like behavior. So the observation and following inference of all these experiments established the particle nature of, the wave nature of particle, and it could now be said that matter also has dual character. Okay, you must remember that Louis de Broglie, who gave his hypothesis in 1924, got the Nobel Prize for his hypothesis when Davison and Germer proved the presence of these waves in 1927. So he got his Nobel Prize 3 years after he proposed his hypothesis regarding the matter wave. It's also called the de Broglie wavelength. And therefore now we can conclusively say that just as light has dual character, so does matter has dual character. So now began the quest for this matter wave. What kind of a wave is this? Is it similar to the electromagnetic radiation that we are so familiar with? So Niels Bohr gave the principle of complementarity, which said that wave and particle models are complementary to each other. Just as matter and energy are interchangeable, are complementary, similarly waves and particles, the models are complementary to each other, and you cannot say that radiation or matter are simply waves or simply particles. So you need a general model which describes both of them. Okay? And this general model is formulated by the probability interpretation. We'll talk more about probability in our later classes. Now this probability interpretation was given by Einstein for the particle nature of waves. Okay? He used statistical mechanics. So Max Born used the similar probability interpretation for the wave nature of particles. What did Einstein do? He used statistical treatment of radiation, and you'll do this in detail in B.M. Sir's quantum theory class. So I'm not going into the detail of this. And what he did was he replaced the exact number of photons by their average number. So in the same line, Max Born used the same statistical model for matter, and he used a function, he incorporated this model in a function that is going to represent the de Broglie wave associated with a particle. Okay, remember the pronunciation is not de Broglie, because you can see the spelling is de Broglie. It's a French name, the pronunciation is de Broglie. Okay. So we are in search of a function which will incorporate this probabilistic statistical model and may be associated with the wave that is associated with a particle. All right. Suppose this wave, a particle is moving, and suppose that the wave associated with that moving particle is given by the common wave function, which we all know, the function representing a progressive wave, psi equal to a sine 2 pi x by lambda minus vt. This is v, okay, velocity of the wave. So you can identify this with this expression, which you have thoroughly studied in your physical optics classes. Remember when we analyzed mathematically interference or diffraction, we used to represent light as the electric field of light as such a function. And if you recall, we denoted mod E square, the amplitude of this wave, as the intensity of radiation. And the same thing was done by Einstein when he was using the particle treatment of radiation. All right. So in the same manner, we can say mod psi square should play the similar role in case of matter wave, since we are using the same expression for representing the matter wave. So using this, Born gave the probabilistic interpretation, which said that this function, this quantity mod psi square, gives the probability of finding the particle within a given interval in space at a given time. We'll discuss more on this in detail in our later classes, but for the time being, just remember that Born interpreted the wave function in such a way that whatever be the function, it may be this, it may be some other thing, but the modulus square of the function has to give the probability of finding the particle within a given interval at a given time. Okay. This is the exact statement of Born interpretation. I'm not going to read it out, but this is just for your knowledge that I gave this in the slide so that you can read through and know what it says. Okay. So it must be a function which should have a high value where the particle actually exists, and then its amplitude must decay where the particle does not exist, because after all it is a particle. It cannot exist at one point of time in more than one place in say the along the x coordinate, okay, or in space, three-dimensional space. So now we have a major switch over when we are doing quantum mechanics, that is, from deterministic we move to probabilistic. And so comes in Heisenberg's uncertainty principle, which once again will be done by BM sir in his quantum theory class. So I'll just mention what it is. It just says you have to remember that simultaneous measurement of position and momentum is not possible with 100% accuracy. If you measure position and momentum simultaneously at the same point of time, then this relation limits the accuracy up to which you can measure each one. Delta x is the error in position measurement, delta px is the error in momentum measurement, and the product has to be greater than equal to h cut by 2. Clear? So, the wave function representing a free particle, what will it be like? Suppose we consider a particle of mass m, momentum px, and it is moving freely, of course non-relativistically, in the x direction. Now you see the moment I say it has a momentum px, it means that I have no error in the momentum measurement. Someone's mic is kept unmuted. Please can you mute your microphone? Whoever has unmuted his microphone, please can you mute it? Okay. So the moment I say it has a definite momentum, it means delta px equal to 0. Now if you look at this expression, if delta px is 0, what is the value of delta x? Can someone tell me? If delta px is 0, what is the value of delta x? Can someone unmute and tell me?
Infinity.
Infinity, infinite. So the moment you have a specific momentum, you don't know anything about the position of the particle. When you don't know anything about the position of the particle, it means that the particle may exist anywhere between minus infinity and plus infinity. All right. So, I mean, that we would not want, because we know that when we see a particle, we do see the particle, be it in the microscope, be it in a collider, but we actually can see the particle. So a wave function that results in the fact that the particle might exist between minus infinity and plus infinity with no exact position is not really desirable. Okay. Now de Broglie hypothesis gives lambda equal to h by p, whereas Planck's hypothesis gives nu, the frequency, is equal to E by h. So now what we do is we introduce new parameters. One is called h cut, h by 2 pi, and one is kappa, the wave number, 2 pi by lambda. So we write momentum. We have already done this, so I'll just quickly. We can now write momentum px as h cut kappa and energy as h nu. Okay, h cut nu. So what have we done? Basically, momentum and total energy are particle parameters, whereas wavelength and omega, the frequency, are wave parameters. So from these expressions, we have expressed momentum and particles, that is, momentum and energy, that is particle parameters, in terms of lambda and frequency, that is wave parameters. So the particle now, since has a definite momentum, so it can be anywhere on the x-axis and can be represented by a plane progressive wave function. The plane progressive wave function is something like this. You all know the expression of a plane progressive wave. I have written the complex form, and we've replaced omega and kappa by momentum and energy because we are actually talking about a particle, so we better use the particle parameter. As you can see that this is a complex function. So how do we justify that a complex function is representing a physical particle? The interpretation of this complex function, how it might represent a real physical particle, comes from the probabilistic point of view of quantum mechanics. Okay, and in 3 dimensions, the wave function looks something like this: a to the power I by h cut p dot r minus et. Alright, so this is the wave function with which we'll work for the time being. Later on, of course, we'll see how the probabilistic interpretation gives us the physical meaning of this wave function. Okay. So now what we'll do is we'll see, we all know the wave equation which gives us the expression for the electromagnetic wave in case of energy, that is light, let us say. We now want to see which is the wave equation that is going to give us the expression for the wave that represents a particle, a moving particle that is associated with the particle that is moving. That is, we want to see the wave equation that gives us the expression of a de Broglie wave. So what do we do for that? We consider a particle of mass m. Okay, so from this is no longer recapitulation. This is new that we are going to do in our present class. This is new material that you are encountering now. The derivation of the wave equation for the de Broglie wave. We consider a particle of mass m which moves non-relativistically in the positive x direction, and it is moving under the action of a force field Fx. Okay, it may be the gravitational field, it may be an electrostatic field, whatever. Of course, the force field is such that the potential does not explicitly depend on time, because for the time being we are not interested in the time dependence of the force field. We want only a force field which is space dependent. The Fx is basically a conservative force field. It can be, as I said, gravitational or electrostatic or some other conservative force field under which the particle is moving. So, the total energy of this particle is kinetic plus potential. Kinetic energy given by p square by 2m, momentum square by 2 mass, and potential is V. V, the potential for the force field F. So total energy E is px square by 2m plus V, which is a function of x. Now what we do is this equation 1 we multiply throughout by the function psi. We multiply the entire equation 1 by the function psi. Okay, please follow very carefully and please stop me and ask me questions if you find anything that you don't understand here, because this is very basic of what you are going to require throughout your study of quantum mechanics until you are doing BSc and later on if you continue with physics. So we multiply the total energy expression on both sides by psi, and then we recall the expression of psi, a to the power I by h cut pxx minus et. So if you differentiate this with respect to x, you get del psi del x, partial differentiation because it is a function of t2. So first you differentiate with respect to x and you get del psi del x as I by h cut px psi. which means if you differentiate once again with respect to x, you'll get del 2 psi del x2 as minus px squared by h cut square psi. Clear to everybody? Del 2 psi del x square equal to minus px square by h cut square psi. So we can write px square psi equal to minus h cut square del 2 del x2 psi. Okay, and we get equation 4. Clear to everybody? How we get equation 4? Just differentiate 3 with respect to x. Next what we do is we again differentiate 3, but now with respect to t, the time. So we get del psi del t equal to minus ai by h cut e to the power capital E to the power minus I by h cut pxx by minus et. So what we really get is minus I by h cut e psi, or e psi by ih cut, taking I downstairs and removing the negative sign. So what do we get? We get, by differentiating with respect to x, we get del 2 psi del x2, and by differentiating with respect to t, we get del psi del t. Or in other words, e psi equal to ih cut del psi del t. So using 4 and 5 in equation 2, so we use equation 4 in equation 2. See, I have given the arrow to replace px square psi, and we replace 5 in equation 2 to replace e psi, and what we get is, from equation 2 we get minus h cut square by 2m del 2 psi del x2 plus b psi equal to ih cut del psi del t. Please just go through the steps once more. All the steps are there now. Can you all understand how I have arrived at this equation? Just tell me yes or no.
Yes, ma'am.
Okay. Of course, when you do it, on your own, on an exercise copy, then the things always becomes clearer, because you'll get to know if you really understood or not. But this is very, very simple differentiation. Just differentiating a function first with respect to x, get the result, then with respect to t, result, use the two results in the original energy equation, and you arrive at this equation. Now this equation is of utmost importance. Okay, you are going to require to know this equation like the back of your hand for your entire tenure of undergraduate physics, and later on if you continue with physics. This, the Schrodinger equation. Okay, the equation that governs quantum mechanics. So if you need to know quantum mechanics, if you need to do derivations and problems in quantum mechanics, you need to know Schrodinger equation by heart. Of course, not learn by rote. You should understand the terms. I've just explained the terms. One comes from momentum, one comes from the force or the potential under which the particle is moving, and the third term, the right hand side term, comes from the total energy expression. This is Schrodinger equation. This is nothing but an expression for conservation of energy. Total kinetic energy plus potential energy is equal to total energy. Okay, so Schrodinger equation. So please try to realize that just now in this particular slide, you have probably derived and been introduced with the most important equation of physics in your undergraduate course, the Schrodinger equation. All right. Okay. So moving ahead, we now study a bit more about the Schrodinger equation, how to solve it, and so on and so forth. So this is the Schrodinger equation. We call it equation number 5, and as I told you, you have to know this equation by heart. Write it down several times, derive it from the first principle several times, like I have done in the previous slide, and get thoroughly acquainted with it. Okay, you should know Schrodinger equation very, very well. This is going to be your friend for the rest of your undergraduate tenure. Whatever quantum mechanical problem, you need to solve it using this equation. Okay, so this is the time-dependent Schrodinger wave equation in one dimension for a classical particle moving in the positive x direction under the action of a conservative force field. So this is like some sort of a definition that we used to study back in school. This is what this equation is all about, the pink patch that I've written on the right of the slide. Of course, you can write this equation down in 3 dimensions too. I'll derive that later on. In 3 dimensions, you just replace the del 2 del x2 by a Laplacian del square. Recall your vector analysis classes. So this is the equation in 3 dimensions. Everything else, doesn't depend on x. So v, you just instead of vxt, you write vrt. Del t remains as it is. Only del 2 del x2, which was in 1 dimension, is replaced by Nabla square or Laplacian in the 3 dimensions. Okay. Now, since we are considering a free particle moving in the positive x direction, therefore we must remember that there are no external forces. If you are saying this is a free particle, it means it is free from any forces. There are no forces acting on it, no electrostatic, no gravitational, no nuclear forces. Of course, you might say, but ma'am, that is totally unreal. That cannot happen. Any particle in this universe has to at least experience gravitational force, because it cannot be anywhere in the universe. It cannot be free of the gravitational force too. So yes, this is an imaginary thing that we are talking about, something fictitious, but this is the simplest case of Schrodinger equation that we can have, and so it is worth the study. The results are worth knowing, that what would happen if the particle would actually move in a totally force-free region, if it was actually totally free. So what happens for a free particle? There is no potential. Since there is no force field, so there is no potential due to that force field. So V is 0. Just a second, I am getting a call. I'll check who it is. Hello? Yes? Yes? I am having a class right now. Please call me up later on, and Kanyashi's forms you'll get only after college reopens, not now. Okay? You'll get a notice. You please keep checking the website. I'll give a notice once it is ready. Okay? Okay. So free particle means force free region, which means there is no potential. V is 0. So in above equation, what will happen? V becomes 0. So the time dependent Schrodinger equation for a free particle in one dimension is simply this. Minus h cut squared by 2m del 2 psi del x2 equal to I h cut del psi del t. We are going to solve this equation, and we are going to solve this equation too. So these three are equations that you should, like, you can write it on a paper and stick it on your wall in your room, because you are going to require these several times. So you better know these equations very well. And as you saw, that Schrodinger equation basically is a partial differential equation, right? Go back a bit. So whether it is in 3D or in 1D, you can see that it is a partial differential equation, and our function psi is a function of both x and t. So can be separated into the time dependent and time independent part. So now you have to recall a bit of your differential equation classes, mathematical physics, that TG had taken in first sem, where you learned the separation of variables method. And I'll recap for you once more. We'll actually separate Schrodinger equation into the time independent parts. Of course, the condition that we assume for doing this is that the potential for a non-free particle is also not a function of time. For a free particle, there is no potential, so we need not worry about it. Our life is good. But if we are talking about a non-free particle, for example, if the particle is actually moving in a gravitational field and we are considering it for our problem, or in an electrostatic field, or most likely in a nuclear field, because quantum mechanics is mostly about dealing with particles in the subatomic or subnuclear cases, then the potential we have to assume to be not a function of time, so that we can use this separation of variable technique. So let us suppose that capital X is the time independent part and capital T is the time dependent part. All right. So we can write the wave function psi, which is supposed to be the solution of Schrodinger equation, as a product of x and t, capital X and capital T. Okay, psi is a product of capital X and capital T. So for motion in 3 dimensions, psi is actually psi rt instead of psi xt. And then we can write psi as a product of capital R and capital T, where capital R is a function of R, the space coordinates, and T is a function of time. All right. So we have in equation 6 in Schrodinger equation, the 3-dimensional Schrodinger equation, what have we done? We have simply written psi as the product RT. Okay. Since del square is a function of x, y, z only, so here t comes out and we have only r within the bracket. And again here, since we are differentiating only with respect to time, so capital T is here and capital R comes out because it behaves as a constant. You know these rules of partial differentiation. So now what we do is we multiply this whole thing by the reciprocal of the product of R and T. We multiply this by 1 by RT. So what do we have? We have minus h cut square by 2m 1 by r del square r plus v equal to ih cut by t dt dt. Remember to replace the partial derivatives by the full derivatives. Okay, do not do a mistake over here. Don't write partial derivatives over here, because now t is a function of capital T is a function of small t only. Okay, so we get this. You can see that the left hand side is a function of r only and the right hand side is a function of t only. So we have done the basic separation of variables. Now, for the time being, we continue with the one-dimensional case only, so that we replace the Laplacian by d2 dx2. So this becomes our equation in one dimension, and we multiply it by 1 by xt, so that we get this h cut square by 2m 1 by x d2x dx2 plus v equal to ih cut 1 by t d capital T dt. All right. So the left hand side has x dependence only. This is the time independent part. The right hand side has t dependence only. So this is the time dependent part. And since x and t are themselves independent variables, x and t do not depend on each other, so each side of equation 9 here can be equated to a constant. And that constant over here, of course, will be the total energy E of the particle, because you know, no matter what happens, the total energy E of the particle will remain constant. There might be some changes in the kinetic and potential parts, but the total energy will remain constant, and each side of equation 9 therefore can be equated to a constant, that is the total energy of the particle. So let us check the time dependent part. This is the equation. We transpose and get something like this. So you integrate and get the time dependent function as constant into e to the power minus I e by h cut t. You can see it is an exponentially decaying function. The time dependent part of the solution of Schrodinger equation is given by this equation, and it is an exponentially decaying function. Alright. Whereas if you take the time independent part now, this is the equation that we are supposed to solve, and we take a transpose and we write it like this. So this is the one-dimensional time independent Schrodinger equation for a single particle. Once again, equation 11 is very important, because mostly you will be given problems which are independent of time, and you have to use this equation to solve for the required function. Okay, so you can appreciate the fact that Schrodinger equation for quantum mechanics is like Newton's second law of motion for classical mechanics. What did you do in classical mechanics? You were given a force condition under which the particle was moving. You used that force to solve second law of motion, which is a second order differential equation, and using the boundary conditions given, you used to get a function which would give you the trajectory of the particle, the path of movement of the particle. Here in quantum mechanics, Schrodinger equation plays a similar part. You are given a force from which you get an expression for the potential V. You use it, solve for Schrodinger equation, get the solution, and that solution will tell you what is happening to the particle that is moving, how the wave associated with the particle is being modified, how it is behaving under quantum mechanical condition. So this one-dimensional time-independent Schrodinger equation is the one that you need to solve. Okay, and the corresponding solutions that you get are called the time-independent wave functions, or since they are independent of time, they are also called the steady state wave functions. All right. Okay, so this is the time independent Schrodinger equation. You rearrange it and you get something like this. You keep the right hand side as 0. So this is the equation that you need to solve. You can see clearly that this is a homogeneous second order ordinary differential equation, right? All of you are familiar with this form, a homogeneous second order ordinary differential equation. Okay, so the final function psi, which is a product of x and t, will be the time function which we already obtained as c1 e to the power minus I e by h cut t multiplied by x, the solution of equation 12. So if you use the value e equal to h nu or e equal to h cut omega, then in the expression of psi you get c1 x e to the power minus I omega t, which becomes just x e to the power minus I omega t if c1 equal to 1. So what is this? This is a particular solution for a particular value of the constant E. Since all of you have done differential equation in SEM 1, I assume you know the terms particular solution and general solution. So if you take the constant C1 to be 1, you get one particular solution for psi, and that of course belong to one particular value of the constant E, the total energy. How do we get the general solution? Of course, the general solution will be obtained by considering the various such particular solutions for the different values of the total energy. The system that we are considering can have different values of the total energy under different conditions. So the general solution will be a superposition of all these particular solutions. So what will be the general solution? A sum of all the particular solution. Okay. Can you all recall from your ordinary differential equation solutions that you had done in your first sim? If you can't recall, then please go through the mathematical physics notes. Any question? Does someone have a question? Someone has unmuted. You have a question? Okay. So do you understand what I have done here? I have simply taken the sum for all the constants Cn belonging to n different energy values, and each energy value giving me a particular solution xn. So the sum of all these will give me the general solution psi. Okay. So this is, so under different conditions given for the force, you get different V's. From that you will get different expressions for X and different values of C, and you will get a value of the wave function psi as a solution of Schrodinger equation. Alright? So this again is important because this is the expression for the general solution. Okay. Now we'll just end this class with the three-dimensional. Any questions till here? Any doubts? Any questions? Please let me know. If not, then we'll just end today's class with the final slide, the three-dimensional wave equation. So in 3 dimensions, we can write the momentum p squared as p dot p, that is px squared plus py squared plus pz squared. So in the expression of total energy that we had, E psi equal to P psi by 2m plus V psi, we replace P square by Px square plus Py square plus Pz square. Now we have this expression of psi where we also replace P by Px plus Py plus Pz. Therefore, if you take del psi, if you differentiate with respect to x twice, you get px square psi equal to minus h cut square del 2 psi del x square. Similarly, you will get for py square psi and you get for pz square psi. And then we have e psi equal to ih cut del psi del t. We have this from our previous knowledge. So using these two, we can write this energy equation as minus h cut squared by 2m del 2 psi plus v psi equal to ih cut del psi delta. I had already written this three-dimensional wave equation previously. Now I just show you how you get it from the one-dimensional wave equation, from the expression of energy. Okay. So this again is very important. This is Schrodinger equation in 3 dimensions. Alright. So we'll move deeper into the solutions of Schrodinger equation and the interpretations of the solution, the physical interpretations of the solutions in our next class. For the time being, please go through the notes the notes contains more than what I have covered in today's class. Go through the notes, go through the slides that I'll be sharing with you and the video lecture if possible. And please, if you have any doubts anywhere in this lecture, please feel free to contact me. Send me a mail, write me a question in WhatsApp, but please clear your doubts, because this is a very important part. This is the absolute basic of quantum mechanics that we are doing, and you need not keep any doubt over here, because this is the portion on which your next steps of quantum mechanics of Schrodinger equation will be built upon. So please don't keep any doubts regarding this. Be very clear in your concepts. Any question, please ask me during class, in your next class, which we will have on Friday, or between today and Friday. You can send me your questions and I'll answer them either through mail or WhatsApp, or we'll discuss if the question is very relevant for the class. I feel I'll discuss it in class, in our next class. Is that all right? All right, everybody?
Yes, ma'am.
Okay.
Yes, ma'am.
So please go through the notes and the PPT. I'll be sharing them by this evening. I'll be sharing the notes and the PPT, and I'll also try to upload the class on YouTube, so that if I share the link, you can go through whatever I say. A lot of things during class which are not written down in the notes, so you can always go back to the video. If I miss anything in the notes, then you can just play back the video and listen to it. It's the advantage of the system that we're having today. Of course, I don't know if we are starting college from 1st December or not. If we do, then we'll resume our physical classes. If we don't, then this will continue. Just to give you a, I don't want to confuse you, because we still don't have any written notice, but the news that is doing the rounds is that there is a possibility of conducting exams between 24th November and 24th December. I still don't know the mode of exam. I still don't know the modalities of the exam, but we have heard, again, don't keep this on record because we don't have any written notice, but we have just heard that between 24th November and 24th December, the mid-semester exams might be conducted. So keep yourselves prepared. I mean, don't just throw away your second sem materials. Keep the 24th November date in mind and keep studying your second sem materials, because you never know, one maybe they just give a 1 week notice time and announce that they are taking exams, and if they open colleges, then it might not be online too, so we don't really know. So this is just for your information. I thought that you must know this, to be prepared, just for being prepared, so that if they suddenly announce something like that, you are not taken aback, you are not taken on a back foot. Okay, so just keep this in mind. All right, okay, then I'll leave the meeting now. Stay well, stay safe, everybody, and we'll meet again next Friday, this time next Friday 2 p.m. All right.
Okay, ma'am.
Yes. Okay. Okay, bye then. And please send me your attendance in WhatsApp. Please send me an attendance, a list of students who attended the class. Whoever, someone please take charge and send me the list, like you all always do. Okay? Okay. Bye bye.